Hello. Previous video we looked into the structure of the polymers. In this video we look at a classification of common polymers. So we will use the structure to help us define or classify these polymers. We will classify them into three categories called the thermoplastics, thermosets and the elastomers, and the way we classify them is by the kind of bonds they have between the chains. So, for thermoplastics we say that they only have secondary bonds, meaning low energy bonds. So, in the case of thermosets they have secondary as well as the cross-link bonds. So, both primary as well as the secondary bonds are bonding the multiple chains together. But whereas in elastomers we see that there are no secondary bonds, which means they have already melted, and what we have is only cross links, and that too they are very few. We will see the differences in these bonds do affect their mechanical properties, and with examples we will see how it affects the mechanical properties. So, we will start with thermoplastics. So, these are also called as linear polymers. As we have seen previously, what do linear polymers mean? They mean that the bonds between polymer chains are secondary bonds which are weak. So, the secondary bonds are the ones which are holding the chains together. But now let us see what happens when we heat these polymers. When we heat, they soften. The reason why they soften is because we said these secondary bonds are weak. So, when we heat they are melted. So, once the bond is melted or gone, then these polymers are free to slide against each other. When they are free to slide against each other, which means that the polymer is becoming softer. So, actually thermoplastics are reusable. The reason why we call them reusable is once you mold them to a particular shape, after that if you want them to mold them to a different shape, only thing you need to do is heat them so that these molecular chains are flowing past each other, which means they form a viscous fluid, and from that viscous fluid you again mold it into a new shape. So, that is actually good because this helps us in sustainability, meaning there is less wastage of this thermoplastic. We can reuse them into different shapes. And there is a very important point to be made here. Usually there is another name for polymers called plastics. People interchangingly use polymers and plastics. This plastics name is coming from here. When we say thermoplastics, people simply call it as plastics, and this name is commonly used for all the polymers, but strictly speaking these are just a category of polymers. Okay. So, in addition to these linear chains, we also have these branched chains. Previously we have seen when do we get these branched chains? When we have this trifunctionality. So, for example, let us see here. So, maybe at here there is a trifunctionality, that is the reason why it branched into two. Same thing is here, here, here and many other places. But what is to be noted is, in addition to these trifunctionalities, there are also secondary bonds. So, crossover here is a secondary bond, means there is a low energy bond between these chains. That is one which is holding these branches together. So, which means there are many branches, but then these branches are held together using these secondary bonds. So, now let us also see how these polymer chains pack together. So, there are two ways they can pack. One is crystalline and amorphous. Actually these are terms borrowed from metals terminology. So, when we say crystalline, what we meant is it is an ordered, and amorphous is disordered. So, what do we mean by ordered and disordered? So, crystalline, as we know for metals, Usually we might have heard about BCC, FCC, body centered and face centered cubic lattices. What it means is all these molecules are very closely packed together in a very orderly fashion. That we call it as crystallinity in metals. But when we use the same terminology for polymers, what we mean is usually these polymer chains fold against each other. So, for example, something like this. So, then there is an order, because now we are taking this random polymer chain and then we are trying to bring some order into these polymer chains. So, for example, if we look at this schematic, this is a crystalline, but and this is another crystalline, let us say this is another crystalline, all these are crystalline regions. But in addition to these crystalline regions, we also have amorphous regions. Let us say this is an amorphous region between so what we mean by amorphous region is these disordered polymer chains. These disordered polymer chains we have between these crystalline regions. So, in general, whenever we say that there is a crystallinity in polymers, it is not as though they are 100% crystalline. Usually they are only partially crystalline. And this ratio of crystallinity is very less, usually in the order of 25% or 50%, or even at most in a very extreme cases it can go close to 80%. So, a classic example of showing this crystallinity is polyethylene again. So, there is low density polyethylene and high density polyethylene. So, low density meaning that there is less crystallinity. Because of less crystallinity, there is more space required to occupy the same polymer chains. But now if there is more crystallinity and there, for example, HDPE, high density polyethylene has 80% crystallinity, which means there is more order, so it occupies less space and therefore the density is high. So, we will see later that there are few thermoplastics which are partially crystalline and few they do not have any crystallinity, they are perfect amorphous polymers. So, let us also explain this crystallinity using an example. What I am trying to show here is, maybe you have seen these old computer sheets. So, the way these are all stacked these are continuous sheets, but they are very stacked orderly. Because they are stacked orderly, they take very less space, but of course if you open them apart, then they take a lot of volume. This is just to give you an analogy about what crystallinity means in polymers. So, we will look at few examples of thermoplastics, starting with polyethylene. Polyethylene, as we have seen, is C2H4 and it is used in tubings, film, bottles and cups. Next we look at polypropylene. Polypropylene, as you can see here, the major difference is it is very close to polyethylene, only difference being that hydrogen here is replaced with CH3. So, CH3 is a radical group which replaces one of the hydrogen atoms. So, in short we call it as PP, meaning polypropylene. So, polyethylene is very similar to polyethylene as seen in the chemical formula here. The only difference is it is a bit lighter and stiffer. That is the reason why it has replaced polyethylene in most of the applications. Next we look at polytetrafluoroethylene, in short PTFE, and Teflon is the commercial name by which most of us know this polymer. We use it in non-stick pans at home and they are also used in bearings and seals. The hydrogen atoms are replaced by fluorine. Fluorine is a non-sticky atom, so that is the reason why it is used as a solid lubricant, and That explains why it is used in lubrication free bearings and seals. So, next we look at PVC. Again here too we are replacing hydrogen with chlorine atoms. So, PVC we heard about in pipes and windows where they are used commonly. Next we look at polystyrene. In the chemical formula we have replaced the hydrogen atom with this C6H5, and the commercial name for this is thermocol, which we have seen, which is used in the packagings. So, polystyrene has applications in cheap moldings and packagings. Finally, we look at polymethyl methacrylate, in short PMMA. This is a commercial name is plexiglass. This is a strong polymer which is like glass. So, it is used in aircraft windows and many other applications. So, if we recall from previous slide, we were discussing about partially crystalline and amorphous. We noticed that the first three, polyethylene, polypropylene and PTFE, they fall into the category of partially crystalline, whereas PVC, polystyrene, sorry, this should be S, polystyrene and PMMA, they fall into the amorphous thermoplastics. So, what we see here is not all thermoplastics are partially crystalline or are they amorphous. They vary depending on their chemical structures. If the chemical structures are simple, they fall into these partially crystalline, whereas if the chemical structure is slightly complicated, then they follow these amorphous forms. So, now let us move into the second category, which is the thermosets. They are also called as network polymers. The reason why they are called as network polymers is because usually they form a network with these covalent bonds. So, the kind of bonds between polymer chains is cross-linked, as already shown here, but in addition to cross-link they also have the secondary bonds. So, let us look at this example of a lightly cross-linked, where we are showing here these are the cross-links, but in addition to these cross-links we also have secondary bonds like places like this, where there is crossover of the chains and there is a secondary bond binding them together. Now, let us see what happens when we heat these thermosets. When we heat them, they decompose. So, let us step by step understand what happens when we heat. So, let us say we are heating this cross-linked polymer. First, because of the nature of the secondary bonds, they first melt. After they melt, the polymer becomes slightly softer, but then the heat probably is not sufficient to break these cross-links or the covalent bonds. Since they are not able to break these covalent bonds, that structure or the shape of the polymer is retained. Though the secondary bonds are melted because of the cross links, the shape or structure of the polymer is maintained. But what happens if we continue to heat? If we continue to heat, then there is enough energy to even break these cross links. Probably you might have seen or sensed this burning of tires. During when there is a burning of tires, we have a smell. What is this smell coming from? Because the polymer is decomposed, meaning the polymer chains are broken at the covalent bonds, and when they are broken at the covalent bonds, they just are too small so that they are dispersed in the air, and when we smell, that is the kind of sense we get. So, I hope now you understand why we say that when we heat the thermosets they are decomposed. So, this is the reason why they are categorized as irreversible. Meaning that once you take a shape for these thermosets, after its use, if you want to reuse, you cannot change the shape of it easily. And actually this is the primary reason why it is not well suited for sustainability aspects. But the reason why thermosets are very popular is because of these crosslinks or the networks. These polymers are much stronger compared to thermoplasts. Because these are much stronger, they are used in the structural applications. So let us see that through some examples. So epoxy is a very commonly used thermoset. These are slightly expensive compared to other polymers. These are mostly used in adhesives and FRPs, like the fiber reinforced plastics. So these are used as the matrix materials for reinforcing the fibers, which are commonly called as fiberglass as well. But in addition to epoxy, there is a cheaper alternative for it, which is the polyester, again used for fiber glass and laminates. So it too is a thermoset, meaning these are strong, but these are not as strong as epoxies. Another example is the formaldehyde, which is used for molding and hard surfaces as well as for electrical fittings. In few videos back, we said that electric fittings, previously people used bakelite, but then formaldehyde has replaced those bakelites for electrical fittings. So now let us move into the last category of these polymers called the elastomers. Now let us see how they are different from the other two. So we start by saying that they are almost linear polymers. The reason why we say almost is because they have very few crosslinks. So initially we started with thermosets saying that there is only secondary bonds. Then we went to thermoplasts saying that there are crosslinks but also secondary bonds. But when we come to elastomers, we are saying we do agree that there are crosslinks, but we are saying that they are very few, like 1 in 1,000 or even much lesser. But in addition to that, we also say that they have melted secondary bonds, meaning that there are no secondary bonds because they are already melted. We are talking about the classic example of elastomer is rubber. So rubber is very soft and it can stretch by large amounts. The reason is because these secondary bonds are broken at room temperature, it is very soft because the secondary bonds are broken. But if you cool down, there is a temperature at which around minus 80 degrees centigrade, when this again the secondary bonds form and then the rubber becomes a little harder. But we are talking about room temperature at which these secondary bonds are already melted. So what we have is few crosslinks. So for example, here we see that there is a crosslink here and there is a crosslink here. But in addition to crosslinks, they also have something called as entanglements. So let us see what are entanglements. Entanglements, to picturize, these are like two threads close to each other. So when they come close to each other, they interlock mechanically. There is no bonding or anything, but then when you try to pull apart these threads, because of this interlocking, there is some bond which is trying to not let you pull apart these two threads apart. So these are called entanglements. This happens when you have very long chains. If you have very long chains, a classic example I think is if you have noticed when you go to give an exam, these are these tags, right, the small length tags which are given to tie up those answer sheets. But I am not sure if you have experienced it, but if you take all those tags together and mix them apart, and then if you want to pick one of them from this bunch, it is hard to pick it. The reason is because they get entangled with the rest. The same happens with a long rope. Usually what happens is they coil up against each other and then they entangle. So first we say that elastomers are soft because the secondary bonds are already broken at room temperature and they have very few crosslinks. why is cross linking important? Because they recover the shape. So, which means when you stretch, because there is no secondary bond, it is soft and again there are very few cross links. So, you can stretch by large amounts, but once you leave they come back to the original shape. The reason why they come back to the original shape is because these cross links do not give up. Since there is a cross link, it is like a memory to the elastomer saying that how it needs to come back to the original shape. Not just these cross links, but also these entanglements are almost like a bond. So, these entangles also ensure that after you stretch and unload, they come back to the original shape. Okay. So, this explains how elastomers are different from thermoplasts and thermosets. Now, let us look at few examples of elastomers starting with polyisoprene. It is a natural rubber which is mostly used in tires and rubber hoses. So, this is a chemical structure of isoprene. We will notice that this is very similar to synthetic rubber. So, polybutadiene is the synthetic rubber and the polymer structure is very close except for this difference of CH3 and H. So, synthetic rubber is the one which is used in most of the tires we see around and they are also used in golf balls. The golf balls are usually made up of a harder shell, but inside the shell you have a core which is made up of this polybutadiene. The reason why they are used is because they are highly resilient. They deform a large and come back to the original shape. Another example is this polychloroprene, which is oil resistant, and because it is oil resistant it is used in the seals. Again, if you look at the chemistry, this hydrogen here is replaced with chlorine. So, these are the three commonly used elastomers, but I hope all of you got this message how are elastomers different from other polymers, because they stretch by a large amount. And why do they stretch by a large amount? Because there are very few cross links which are resisting this deformation, but they come back or they have a memory of the original shape because these cross links will pull those chains again back to their original positions as well as the entanglements. So, let us summarize what we have discussed in this video. So, we have classified common polymers as thermoplastics, thermosets and elastomers, and the way we have classified these is based on the bonds. We started by saying that thermoplasts have only secondary bonds. So, when they are heated they soften and these are recyclable, meaning once you heat it, it turns into a viscous liquid and it can be again molded to a new shape. Thermosets, they have secondary bonds as well as cross links, meaning that when they are heated the secondary bonds melt and it softens a little bit but the cross links cannot be melted easily, and the only way it melts or breaks is by giving lots of energy or burning these thermosets. At that temperatures or at that high energies they simply break down. So, when the polymer chains break down, that is called as decomposition of polymers. And the final category is the elastomers, where we said that it has very few cross links like 1 in 1000 or much lesser than that, and we also said that secondary bonds are non-existent at room temperature. But of course, if you keep cooling this elastomer, like if I keep cooling the rubber to let us say around minus 80 degrees centigrade, that is when these secondary bonds are again formed and then the strength or the stiffness of the rubber is increased. And we also explained how the structure of the polymer affects or lets the large stretches which we see with elastomers. So, with this we conclude today's lecture, and in the next lecture we will discuss more about the mechanical properties of these polymers. Thank you.